Welcome to another demo of the MovingAI demo pages. And in this demo today, we're going to be looking at Dijkstra's algorithm. Dijkstra's algorithm, of course, is a well-known algorithm. The paper for Dijkstra's algorithm is from 1959. And today we have a little demo here that allows you to look at to build a graph and to look at how the algorithm runs on that graph. If you're interested in a longer description of that, you can take a look at this best first search video. Of course, this demo video will show up there at some point. And if you're interested in some of the technical details that are interesting, I'd recommend looking at this 2011 position paper by my colleague Ariel Fellner, where he talks about some of the differences between the way that it is taught. Dijkstra's algorithm and some of our other search algorithms are taught in artificial intelligence. So that's always interesting to look at. On this particular problem, you can start by loading a graph and put a default graph in here. You can move nodes around. Notice that the cost of edges don't change based on moving the edges around because the costs are fixed when we add them here. We can also add edges. So I could, for instance, change the cost of an edge here. Or I could clear the graph and I could add my own nodes here. And I can create my own problem or my own problem topology. If I add enough nodes, they start getting a little bit smaller here. And we can do things like, add some connections here and make a problem where we work through that problem or there's some structure to sort of get across this state space. And what you do in here is once I put some edges in, let's put another edge of a different cost maybe here. And can put one here too. So what we can do is, in addition to then basically adding edges, adding nodes, and moving them around, the main thing that we want to do is find a path. So when I find a path, I'm going to choose a start node and I'm going to choose a goal node. And once I've done that, then it's going to give to me my data structures here. So on the top, we have all the nodes that are just listed by their labels here, A through J. And it tells us where it is. So it's on the open list, it's on the closed list, or it hasn't been generated. And then down below, we can see the open list, which is the cost of the state on the open list, the parent of the state, and on the closed list, we'll see something similar. And so one thing that I would really recommend is if you're learning Dijkstra's algorithm is you can put some problems in here and you can run them by hand, and then you can validate that your understanding of what happens when running by hand is the same thing that happens as the algorithm runs here. The other thing that we can do here is we can watch and just check our data structures and look at what's going on. Let's go ahead and step this search and walk through here, and then we'll come up with another task that we can do that's useful, particularly when we're building our own implementations of the algorithm. So we step the search. We're going to take A here. We're going to expand A. And we're going to generate both of its neighbors. In this case, nodes that are closed are in this reddish color. Nodes that are open are on green. And the yellow state is the node that is on the top of the open list. And the pink state is the goal. So in the open list, we see E with a cost of 1 and B with a cost of 2. This is sorted, so we're going to expand E next with a parent of A. So we can go ahead and step that search. When we do that, that's going to generate D and G. So we've added them, and we're going to continue here. And then we're going to expand B next. We notice that B is going to give us a path cost 3 to D, but D we already have a path cost 2. So when we expand B, we won't see D go back into the open list, but we will see C go into the open list. So we can step the search and watch that. And now we have two nodes, both D and G have the same cost. It's a tie between them. And so we just choose arbitrarily to expand D next. And we can see over here these nodes that have been added to the closed list. Sorry, these are this lighter color of red because it is the start state. So we do know that. And then B and E are also enclosed. And this is in an arbitrary order with the cost here and the parent. Okay, and so now we can see we've closed D. D as a parent of E. So we're continuing to update things. And then we're going to go over to G. And when I expand G, I've generated a lot of different nodes here. And I'm going to have generated I, which is the goal of cost 3. But I've also got C sitting here with cost 3. And so because we haven't actually tested to see if I is the goal yet, we're going to go ahead and expand C. H also has the same cost. J also has the same cost before I finally get to I. And I finish my search, and then it draws the path on top here. So this was a fairly straightforward search that we ran. Should be not too hard, especially if you study the algorithm to watch what's going on here. Something that's interesting, though, is to think about if I'm trying to solve a problem like this, especially when I'm implementing the algorithm, one of the hardest things to do is to get the updates to my data structures working properly. And there's many problems like the one I ran here, where it ends up that if we look at the parents are the first node that expanded or that generated that state. And so what that means is that I'm not doing a lot of updates to my data structures. So it's interesting just for testing purposes to create a problem where I'm going to generate states with a large cost, and then later on I'm going to go and update those costs. And so that's a nice task to do. It's a task that I give to my class to say, hey, change the graph, or depending on the graph you started with, but build a graph where we're going to generate a state with large cost, and then we're going to update the parent pointers to a different parent that comes with a lower cost. As I said, doing so often helps find a lot of bugs in a code implementation. So I'm going to just build a new graph here that's going to be a very simple example of where this can happen. This will be our goal down here. And what we're going to do is we're going to put an inexpensive cost path that goes right here. And then we'll go to the goal. And all we have to do here is basically put a really expensive edge right here. So when we do that, then what's going to happen is that we're going to immediately generate C with a large cost. So let's go ahead and find path. I'm going to go from A to D. Oops, sorry. Find path from A to D. And so what I'm going to do is when I step my search, I've generated C with a cost of 9 and a parent of A. And now the next node I'm going to do is B. And so now what I've done is I've taken C and I've updated. Before it had a parent of A with a cost of 9. Now it has a parent of, C has a parent of B with a cost of 2. And one more step and we get to the goal and we're done. So this is just a very simple graph, but it's very useful to try and do this to see what does it take to make sure that my data structures are being updated properly and to test and to validate that with simple problems like this. So it's a great way to see if you understand what's going on. There's another demo that we'll be looking at later that it has the A-star algorithm, and there's some nice comparisons to look between the two algorithms. So I'd recommend, and the demos and what they're doing, I'd recommend going and having a look at that after this one. Thank you very much for watching, and we'll see you again later.